Okay, now I can share the screen.
Yes.
Okay. Okay. YouTube streaming is also on, and streaming. Okay. Can you all hear me now?
Hello.
Yes, sir.
Okay. Great. So let's begin.
कॉलेज में जो हॉल 4 में बैठा हूँ लेक्चर चालू है अभी तो
Okay. I request everybody to mute themselves so that we can. Okay, I'm muting everybody. Okay, I have muted everybody. If you have any questions, you can write on the chat window. I have opened the chat window. Just a minute. Okay. Okay, chat window is there in front of me. Please ask your questions on the chat window. Okay, so welcome everybody. And today is our first class. So it will be mostly about, there is a WhatsApp group link. I don't have WhatsApp, so I cannot use because I'm not on WhatsApp. But if you have any questions, feel free to ask the questions in the Mookit forum. Right? Mookit already has a forum. Oh, just a minute. The microphone. Let's see if this can be used. Okay. Can you hear me? Audio. Okay, can you hear me, everybody? Okay, great. So welcome to the course. Let us start our discussion. So, okay. So first, some logistics about this course. Okay, I'm Vipul Arora. I'll be teaching this course for this semester. This is for the first time we are doing this course, and this course is a PG level course, means mostly we will be having many latest state-of-the-art work, which is discussed here in this course. Of course, we will be focusing on the foundational aspects, but more than that, we'll be focusing on state-of-the-art kind of work, which is popular these days. Okay, so let's start with this. There are many problems in science. For example, that is why we are here, right? We are doing science because we want to solve problems. We want to understand about the nature. We want to get a better model, or get a better worldview, get a better view of the world, so that we can do things in a more efficient way, and we can improve ourselves so that we can become better situated in our understanding. Basically, that's the any human being will naturally have questions about nature, right? And we ask these questions. Animals maybe not very sophisticated questions that they can ask, but human beings can ask really very sophisticated questions. They can try to understand the why we are here, why things are happening the way they are happening. How can I understand this thing so that I can have a better prediction of the whole thing, or I can have a better control over the thing, or I can prepare myself for the coming future. So these fundamental questions are starting from what is space and time, right? What is everything around us? How time is pushing everything? Everything is moving. Then similarly, a very fundamental question which is asked is, what is intelligence, right? How is it that we are able to, first of all, define problems, and then we can formulate them in a way that it can be solved, and then finally we can solve problems. So what is intelligence? And even more fundamental question is, why do we learn at all, right? Why do we learn something? So this is a famous problem called embodied learning. Let's say animals, they also learn things, but they cannot learn in a sophisticated way that we can learn. And also they cannot pass on that learning in the way we can. For example, we go to colleges, universities to learn things. For example, we do not reinvent the wheel. We do not, somebody has invented the wheel, that he or she passed on that knowledge to the coming generations through language. And we are able to today uh, learn that immediately without having to reinvent it on our own. But animals don't have that kind of learning, right? So that is why humans, in a very short span of our life, we are able to learn so much. Whatever, like Newton has said, standing on the shoulder of the giants. So how is it possible? Because we have that language by which the giant or the previous intelligent people, they have passed on their knowledge to us, and we are able to get it. So the question is, okay, if we are learning is very sophisticated, definitely, but why do we learn at all? So this is a more fundamental question. Okay, and then another question, which is a little more pragmatic, or which helps us to do things in a practical way. What can we make machines learn like humans? This is a more pragmatic way of understanding things. Can machines learn just like we humans learn? And what are the peculiar characteristics that make us learn certain things? And if we can mimic them, or we can incorporate those principles in the machines, so can they also uh, imitate intelligence? They can become artificially intelligent in some way. Um, Okay, so these are the questions which have driven us to this subject matter, machine learning or artificial intelligence. So this problem, or this machine learning, is a very interdisciplinary problem. So you can study this area from different perspectives. One perspective is, of course, machine learning as it is practiced these days. We have shallow models, deep models, and reinforcement learning, supervised, semi-supervised learning, and all that I'm sure you have learned in your previous courses, because one of the prereq for this course is basics of machine learning. So I hope you are familiar with those popular methods. And then this whole problem can also be approached from the perspective of optimization. We are optimizing our models to solve certain problem given certain constraints. From statistics, we are doing a lot of statistics to find out useful information from big data. And it can be approached from computer science perspective. See, all these computations are done on machines, right? So can we optimize our machine in a way that it can speed up the computations? For example, we have GPUs, right, which kind of they do parallel processing, so that we can simultaneously process computations, and in this way speed up the computations greatly. And similarly, we can have distributed computing. And these days, people are talking about federated learning, which means because there are privacy concerns, I don't want to send my data to the server where everybody can see that data. So can the models be trained on my device itself? For example, if I have a mobile phone, can the models learn in some way from on the mobile phone itself? And there are challenges like mobile phone has got limited memory, limited processing power. So all these challenges are viewed from a computer science perspective. Then another area which contributes to this whole research is cognitive science. How do we understand things? How do we perceive things? Let's say speech or music. How do we cognize it? How do we experience those things? And similarly, vision. How do we experience a visual sensory input? Then neuroscience. So neuroscience it has a premise, it has a basic understanding, okay, that brain is the seat for intelligence. So can we understand how brain is what kind of processes are happening inside the brain, in the neurons in the brain, so that we can understand intelligence from that perspective. So all of these are kind of different perspectives on this same area, that fundamental question. Okay, how are we learning? Why are we learning? Okay, at least how are we learning, and can we mimic that in machine? Okay, so this was a kind of very broad picture of our subject matter. Next, let's come to a very smaller, narrower question, which is, what is machine learning? So what is machine learning? Machine learning, in a very crude sense, it is, there are algorithms, and algorithms can make computers do specific tasks. And I do not want to make handmade explicit rules, but I want my machine to be able to learn from the data. So for example, I'll give you a very uh, impressive example, which I find very impressive because I experienced this. So there have been, so let's say, take the problem of Alexa. Today you have Alexa or Siri or Google speech recognition in your devices around you. So speech recognition is a very difficult problem, no doubt about that. This problem was seen from a perspective of linguistics or phonetics or um, um, some engineering techniques by which we can make some rules, and then we can try to make machines which can recognize speech. And these rules were made by hand. For example, you look at the spectrum of A looks like this, U looks like this, E looks like this, and you make some simple rules like slope of the spectrum or something like that. And in that way, you try to make a machine which can classify your audio input into different phonemes, and then you string up the phonemes to form words and string up the words to form sentences. So this approach was taken long ago, but then the problem is that there is a lot of variation, a lot of variability in the data. When I speak versus when somebody else speaks then those two are not exactly same. There are many variations, and even more, that when I speak in running speech, let's say when I'm speaking some word, like for example, in Ram. So when I say in Ram, it is very, that looks very different from when I speak in a standalone fashion, just So there is a lot of difference in the two and that makes speech recognition very difficult, because things, when different phonemes come together, they modify each other in very complicated ways. And then, of course, background noise. And so basically, a lot of variability, and handmade rules are not able to handle those things. So can we make machines automatically learn from the data? This is just one example I have given, and I am sure you can find many, many examples for this. So this is roughly the understanding of machine learning. Now, okay, so this is a very simplistic model, which I use to describe, like in the simplest terms, if somebody asks me what is machine learning, so we can say machine learning means we are creating a model so that it maps the input to the desired output. Let's say when there is a speech recognition problem, input is the speech or the speech recorded in the computer, which means your audio waveform, like the wave file, and the output is the text, the string of text, which tells what was spoken. So that is the very simplistic definition of machine learning. We have a model which does what we want it to do: speech recognition, or image recognition, or video recognition, or some kind of signal processing, or reinforcement learning. So basically, this is simplistic visualization of machine learning. Next, okay, this is a nice video on. Let me see if I can play the entire long video, but I I recommend this video for you to watch later.
DARPA has always been at the forefront of artificial intelligence, driving the technology forward. So it's no surprise that we have some pretty definitive views as to where it's headed. There's been a lot of hype and bluster about AI, talk about a singularity that AI will exceed the capability of human beings, maybe even displace humanity. We're going to take a much more level-headed approach and attempt to demystify, talk about the technology, what it can do, what it can't do, and where it's headed. I think it's helpful to think about 3 waves of AI technology. The first wave was handcrafted knowledge. Here, experts took knowledge that they had about a particular domain, and they characterized it in rules that could fit in the computer, and that the computer could study the implications of those rules. Examples of this are logistics programs that do scheduling, game-playing programs like chess, or even TurboTax that you might be using to do your taxes. In the case of TurboTax, for example, you have experts who are tax lawyers, tax accountants, who are able to take the complexities of the tax code and turn them into certain rules, and the computer then is able to work through these rules. And this kind of logical reasoning is very typical of these first wave systems. They're very good at being able to take the particular facts of a concrete situation and work through it. But they're not very good at other dimensions of intelligence. Other dimensions include, for example, the ability to perceive the outside world and see what's going on. In TurboTax, it can take a W-2 and make sense of it, but that's about the limit of it. It's also no good at learning, and learning is a major part of intelligence. And there's another characteristic of intelligence that we don't see in these first wave systems, which is abstracting. That is taking knowledge that they've discovered at a certain level and applying it up at another level. So what we found with these handcrafted knowledge first wave systems is that they enable reasoning over very narrowly defined domains, but they have no learning capability and poor handling of uncertainty. But that doesn't mean that these first wave systems are old and tedious and boring. We just had some great success this year in cybersecurity, where we had systems that were based on first wave principles, be able to study the code within a computer and be able to make sense of, here's a vulnerability, this is what I need to do to fix that vulnerability, there's something that I can do to take advantage of somebody else's vulnerability. So the Cyber Grand Challenge was a great proof that first wave technology is still very relevant. And this leads us to a second wave of AI technology. This wave is characterized by statistical learning, and it's been tremendously effective in doing voice recognition on your phone, for example, or face recognition, being able to sort through all your photographs. Sometimes people say the computer will just learn things, but actually nothing could be further from the truth. There's a lot of effort goes on behind the scenes to create a system that the computer can learn in the context of. In fact, engineers take time to create statistical models that characterize the problem domain that they're trying to solve. And then what they do is they train those statistical models on specific data. The characteristics of these second wave systems is that they're very good at being able to perceive the natural world, being able, for example, to separate one face from another, or to separate a vowel sound from a different vowel sound. They're also very good at learning. By providing them with particular kinds of data sets, they're able to learn and adapt to different kinds of situations. So they're very strong in these dimensions of intelligence. However, in the reasoning, the logical reasoning intelligence that we saw was very strong with first wave systems. The second wave systems essentially have very limited capability, and they certainly give us no new capability to be able to abstract and take knowledge from one domain and apply it dramatically in another domain. So to characterize this current very powerful second wave technologies, we would have to say they have nuanced capabilities to classify data and even to predict the consequences of data, but they don't really have any ability to understand the context in which they're taking place, and they have minimal capability to reason. I think it's worth digging under the surface a little bit to understand a bit better why these systems work and what they're capable of doing and what they're not capable of doing.
Okay, so I think this was this is a very nice introduction to AI kind of overview. So I think you can go through this video later. I would highly recommend it. Let's move on. Okay, so now I'm going to discuss some topics in machine learning which are of interest to us, especially in this course. of course, there are many areas. There are many good conferences like NeurIPS, ICML, etc., where many of these works are being displayed every year. But we can pick some areas which we can take up in this course, or which you are encouraged to do in this course. So one such problem is learning from less data. So you have got, so generally in machine learning, you take lots and lots of data and try to learn from the data. For example, take the problem of speech recognition. You have speech recognition, let's say Alexa or Siri or Google Home. So it seems that they are working very good. They are able to understand what you are speaking, or at least they recognize the words, sentences, the common ones, at least what you speak. But you know how much data is required to train them? It is humongous. It's huge amounts of data. You can imagine thousands of hours of speech is required to train a simple speech recognition system. Simple means which can recognize common sentences like Alexa does. So thousands of hours of data, and it can even go to lakhs of hours of data also. It's so huge data is required. So now the question is, can we learn from less data? For example, human beings don't require that amount of data. For example, to learn a new subject, let's say machine learning, you don't need thousands of hours of lectures. You just, by listening to the concept once and maybe practicing a few problems, you are able to understand that concept, right? So this is the thing, learning from less data. And there are many kind of problems, many popular paradigms within this problem. That, for example, one is few shot learning. Few shot learning means you have got you learn from in the training you have got lots of data for certain classes. Let us say horses and fish, horse and fish. This kind of horse and this kind of fish. You have got many classes, thousands of samples for each class. But you have never seen a zebra. Your training data never contained a zebra. And now I ask you, can you recognize a zebra? Can your machine recognize a zebra? And I give you a few pictures of zebra. Oh, this is how the zebra looks like. Can you quickly generalize, or can you quickly transfer your knowledge from that those classes to this new class? This is called few shot learning. And zero shot learning means I never show you any zebra, but I just tell you, see, just like a horse, it looks like a horse, and it has stripes like some animal, this animal. It looks like a horse, but it has stripes like this animal. That's it. I'd never show you a zebra, but I just tell you some things about the zebra. And you can say, okay, so it has got 4 legs like a horse, and it has got stripes like the fish. It has got no fins like a fish. So this is what the zebra must look like. So this is called learning from less data, or few shot learning. Sorry, this is called zero shot learning. And this is one important problem in machine learning, which you can see. And okay, so I did some work in this area. Let's say in speech recognition. For speech recognition, as I told you, you need thousands of hours of data, and you cannot get this much data for a new language. Let's say for English, definitely now there are free data available. You can just go to internet and download these data sets. It means speech accompanied by what text the person is speaking, so that you can train your machine. This input-output system, the speech maps to the text. But if you go to a new language, let's say I go to Punjab and I want to make an Alexa for Punjabi language. It's very difficult, right? Because I don't have much data for Punjabi. So what I can do is, so what here I did is I took the like this, I constructed attributes for each phoneme of English. And these attributes came from phonological knowledge, which is the linguistic knowledge. These attributes are common across different languages. So same attributes are shared by English as well as Punjabi. So then I transferred the model from English to Punjabi with the help of these attributes. And we showed that, okay, this now the Punjabi model also is able to learn very quickly the new sentences. Okay, so this is the kind of problem which is interesting in machine learning these days. Then next we come to another kind of problems, which is interactive learning or human in the loop. Imagine you are working with Alexa and you are telling some things to Alexa. You ask that something which Alexa did not know. For example, I asked Alexa, um, um, can I add I mean something like that? Can I add dropout layer to my neural network? And Alexa does not know what is dropout. Means Alexa does not have this word in its dictionary. And can you tell Alexa, when I say dropout, it means this? Or let's say you ask Alexa, please ask my friend to go to, tell me some peculiar word. Okay, let's say Alexa does not know some proper nouns in Hindi. Let's say my friend's name is Ram. So Alexa, tell Ram to do this. Alexa will not recognize this word because it has never seen this word before. So you can can you interactively give now, Alexa, when I say Ram, it means this. So humans are helping the machine to learn, and there is a gradual inflow of labels from the human annotators. So let's say you are telling the machine, okay, when I say Ram, it means this Ram. And this learning is not happening all at once, because as Alexa is functioning and suddenly this new input has come, it has to learn or absorb that knowledge and again start functioning. And then again, somebody else will give some new input. It has to again absorb that knowledge and again perform the action. So it is called interactive learning. So basically the machine is improving as the human annotator or the human user is interacting with it. There is one good example. This is from music application. It's a very old example. Means this system is I think 2013.
In this demo, we'll talk about interactive sound source separation. Take for the moment the task of extracting the background layer of an image in Photoshop, in this case, a cloudy sky. To do so, you probably take the magic wand tool, click on the background a few times, and say extract. With the layers separated, you can discard the old background and replace the. Now imagine doing the same process with an audio file. You could remove a noisy cell phone ring from recorded speech, remove a cough from a live orchestra recording, or even separate out the vocals from your favorite pop song and remix it with a new instrumental track. To do these tasks and more, we've come up with a new algorithm and interaction paradigm for single channel sound source separation. And it looks like this. What we have here is a sound source separation editor where we can take a single audio file and separate it into multiple layers, similar to our image example. To extract a layer, we first load a recording into the topmost track. The recording is visualized using what's called a spectrogram display, which depicts the frequency content of the sound over time. Let's take a listen.
Traffic news now, and if you're coming in from London from the south, avoid Tower Bridge this morning. There's an half-mile toll back. Otherwise, traffic's moving pretty freely into London this morning. It's 8:33, 10 degrees, and a nice mild day to start the week.
In this case, we'd like to remove that pesky cell phone ring from the background speech. To do so, we can use Photoshop-like drawing and painting tools to identify the cell phone ring and the speech, and then extract them both. We'll use the color yellow to identify any speech in the recording and the color blue to identify that pesky cell phone ring. I'll use the box select tool to roughly sketch out the speech and then hit the process button to extract. Once separated, the speech layer will appear in the middle track and the cell phone layer will appear on the bottom track. Let's listen to the separated speech.
Traffic news now, and if you're coming in for London from the south, avoid Tower Bridge this morning. There's an half-mile toll back. Otherwise, traffic's moving pretty freely in London this morning. It's 8:33, 10 degrees, and a nice mild day to start the week.
Now let's listen to the separated cell phone. Awesome! But what about more complicated sounds, like removing the bass guitar out of a recorded drum loop? Well, let's give it a shot. I'll load up a funky drum beat and try to extract a drum layer and a bass layer out of this single recording. I'll use the color yellow to select the drums and the color blue to select the bass. Before that, let's take a listen. Now I'll do a little selecting and extract. Once extracted, we can listen to the separated drums and then the bass. Notice that when we listen to the drums and the bass separately, the results aren't perfect. No problem, we can correct for errors in the separated layers by further drawing on the outputs to refine the separation. This will take a little bit of time, but in the end, the results will be worth it. All right, let's listen to the final result. Even more awesome. Well, what else could you do? How about removing the vocals from a...
Okay, so I think you got the idea that how, so in the first run, the machine was not able to separate them very well, but then the human gave some more inputs, and from that, the machine learned, okay, how to improve itself, and the machine did. So this work is, you can see almost 2013, very old work. It is not done with deep networks, but it is done with metric spectrization. Of course, with deep networks, now there is more work going on. Okay, let's go to the next slide. Okay, another area which is popular in machine learning is active learning. What does that mean? Machines can ask human annotator, could you please label this sample? For example, in the previous example, the human annotator himself was choosing what to label, what not to label. But imagine you have got thousands and thousands of data points. Now, how does a human annotator know what should I annotate or what should I label? Human annotator has limited capacity. I want to label only, let's say, 10 samples because it is very time consuming. I don't have much time. I just want to label 10 samples. So, but which 10 samples to take? Okay, you can take randomly. That is what mostly people will do. They will just randomly choose some 10 samples, label them and give to the machine and ask the machine to learn from it. But this is not the best way because, for example, if something the machine is already doing very well and you are labeling it again, machine will say, it won't learn anything from there, right? But if you give machine some samples which the machine is not able to do very well on, then the machine will say, oh, this really helps me. Machine is really able to learn better. That is called active learning. So now the machine itself will present to the annotator, oh, could you please label or annotate these samples for me? Then the annotator will label those 10 samples and then the machine will be very happy and be able to learn very well, right? So this is how it is possible. It is possible by quantifying the uncertainty. Let's say when the machine does not know certain things, then the machine will ask the annotator, can you please answer this for me? Just like when you learn a course. Let's say I'm teaching you machine learning and you don't come and ask me about every paragraph, but you will only ask me paragraphs where you are uncertain. Okay, I didn't understand this point. Can you please explain this to me? Because you are able to quantify your uncertainty, so you are able to come to the teacher and ask, oh, can you please clarify this? And that helps your learning very well. But if same thing can be done by the machine as well, then the machines can also learn much better. This is called active learning. The machine itself tells, okay, these are the samples which I need annotation for. And so that and it is seen practically, like this was our work in, again in speech mispronunciation detection, where the machine will tell, okay, can you please annotate this for me? And we saw that instead of randomly choosing samples for annotation, if the machine gives the samples to learn from, then the learning curve is very fast, means the learning is speeded up a lot. Okay, so, okay, another class of, another interesting problem is imbalanced data or heavy-tailed distributions. So this is an interesting problem, because in real life, for example, if you look at some standard data sets in machine learning, for example, let's take our, what is the data set which has got digits in it? Okay, please write on the chat window. I want to see if people are MNIST. Yes, thank you, Aditya. So MNIST dataset. MNIST dataset has got digits, and for each digit there are fixed number of, or almost equal number of samples given to you, handwritten digits. Let's say 1 is there, then different kinds of 1 written by people are there, and the number of samples for each class is almost same. But in real life, you cannot imagine, you cannot expect that to happen. For example, there are certain classes for which the data will be very small. Imagine you are making a sound recognition system, and now I ask you, okay, please make a sound recognition system which recognizes sounds like car horn versus what else? Car horn versus somebody speaking versus somebody smashing the door, right? So you can very easily collect a data set. You will go to the gate, IITK gate, and you will collect some car sounds, and you will come to your hostel, bang your door and say, this is door banging sound. Then you will go to a classroom where somebody is speaking. You will record the sound. It's very easy to collect this data, and it is very easy to make sure that this data is balanced. But imagine if I give you a class now. Also, I also want to recognize gunshot sounds, like gunshots. And you will say, oh, where will I get gunshots from? So it is a difficult task, right? So what will you do? Okay, you can collect some gunshot sounds, maybe go to NCC, and when they go out for shooting practice, you can go with them and record some gun sounds. But other than that, where will you get gun sounds from, right? So it is a kind of rare data. So the data will not be that much. So when you train your model, it will not be balanced data. And if I similarly ask you for some classes, especially if you see in medical domain, some kind of diseases have very little data, while some other diseases have lots of data. So, and even for images also, you have certain images, certain classes can have lots of data, like faces can have lots of data, but some other, let's say peacocks, in IITK, there are many peacocks, but you cannot click that many pictures as you can click pictures of humans. So imbalanced data is a problem. So I've done some work in this area. This was with Alexa. We were building Alexa Guard. Alexa Guard is basically home security system. Alexa acts like a home security system, and it recognizes some sounds in the environment. So some sounds which are unusual. For example, somebody's walking in the floor, somebody's walking in the room, or somebody's breaking the glass. So we had lots of imbalance in data, and some techniques. Okay, so the strategy which we used is don't oversample. Generally, people use oversampling to handle imbalance. What is the meaning of oversampling? Let's say I have got, for one, let's say there are two classes. One class has got 10 samples, other class has got 100 samples. So what will you do? You make copies of these samples and make them also 100, right? There are 10 samples. You make 10 copies of every sample, then you get 100 samples. So it's like oversampling, but that doesn't help much. Rather than that, you cluster them in an embedding space that improves the performance much more. Anyway, these are the details, but the problem is this, that heavy tail distribution or long tail distribution or imbalanced data. Okay, so now another problem could be anomaly detection. For example, you have got lots of data for normal something, but suddenly there is some anomaly. For example, imagine you have a drone which is doing surveillance of the entire area, and suddenly there is some fault in the drone, so the drone starts malfunctioning. But you have always trained the drone on good data when the drone was functioning very well. You trained the drone to recognize things or do surveillance in a nice way. But now when the drone has started malfunctioning, can you detect that anomaly, that no, the drone is not behaving in the usual way? So you never trained for that, but there is some different kind of anomaly. For example, the drone has hit some obstacle, maybe on the pole or on some building, it has crashed, or maybe some bird has hit the drone, so the drone has shaken or broken some part. One kind of anomaly could be, for example, if you have traffic monitoring system, you are monitoring the traffic and suddenly there is an accident. This is one example. Or there could be machines in the warehouse or machines in a factory, lots of machines installed, and suddenly one machine is malfunctioning because of some fault. Then you never trained for it, right? Because you don't see faults generally in the machines, and suddenly this kind of fault has appeared. Can you do anomaly detection? Oh, there is something wrong with the data and there is something wrong. And can you also locate where exactly this fault is located? Let's say there is a network of sensors and some sensor is malfunctioning. Can you detect that anomaly and finally zoom into the exact location of the anomaly? So these are the problems and which can be looked at. Okay, now another area of current machine learning research is explainable AI. Okay, read this title. Why should I trust you? Explaining the predictions of any classifier. So let's say you have a model, it's more like a black box model. The current deep learning models, especially, they are very kind of black box model. You give some input X, it will give you some output Y. But if you want to ask, why did you make this decision? Why did you give this output only? Then there is no way you can find that out because the network is so complicated and the layers are so many layers and so many neurons and activations, and it's very difficult to find out why did the network detect this? Why did the network give this kind of output? So that is so for this is now where is this important? This is very important where you want to go down deep and find out the cause. For example, this see this in medical applications, you have a model, it has got a lot of data. Let's say some patient is having these parameters, these readings, these symptoms, and then you apply a model on this, and the model will give you the output, oh, this person has got corona, for example. Now you will ask immediately the question, why did the model give this prediction? Can I trust this prediction? So trustworthiness or trust and explainability. Can I trust this model? And I can trust it if the model, if model can tell why it made that decision. So for example, the model will say, oh, I found this particular symptom, which made me think that this person has got corona. Then you will say, oh yes, this. Then the decision maker will be much more confident in making a decision. Otherwise, who would like to trust a machine? So explainable machine learning is a very good area. Now, This is one application of explainable machine learning which I worked at. So I was working on language teaching. For example, if I'm teaching a new language, I'm learning pronunciation of a new language. Let's say I'm a Hindi speaker, I'm learning English. And I make certain mistakes when I speak English. One common mistake could be like instead of saying school, I said is school. Right? Many people when they say school, they will say is school. So this is a mistake as per the English convention. But can the machine detect this mistake, and it can also give feedback to the user that why was this wrong. I will give an example here. So let's say this is a German, when a German person will read I say bag. So generally German people, they don't say g at the end, they say k. Instead of g, they will say k. They will say I said back. This is how, because German has no g ending words, so they make this mistake. And even in English, they carry forward that knowledge. They bring forth that knowledge, and they don't say bag, they say back. I said back. So when my machine will hear this, it will say, oh, there's a mistake here. You said this wrong. But the German person will not understand what was the mistake. So we say, what was wrong here? Then if the machine has got explainability, it can give a reasoning. The voicing should increase for G, for this sound, basically this G. Now, so the user gets an exact input. Okay, so this is the mistake which I made, right? I made a mistake specifically in this location. But then he may not understand what is the meaning of voicing. So you can give further explanation. Voicing should increase for G, just like the first sound in goose. German people are able to see this sound without any problem, and they will understand, oh, this is like goose, like G. So not K, but G. So in this way, you can see how explainability or interpretability, it helps the users to understand why the machine gave a decision. Instead of saying there is a mistake here, you are telling, okay, what exactly is the mistake and how to correct it. So the user can trust the machine much more. Okay, now another area of research could be generative modeling. So before this, whatever we were discussing was mostly from discriminative modeling perspective. So what are discriminative models and what are generative models? I hope you remember from your basic machine learning course. So in generative models, you can you know the distribution probability of X given the class, probability of data given the class. But in discriminative models, the model will just tell you probability of class given the data, probability of Y given the X. But in generative models, you have probability. You also know the distribution probability of X given the class. And you can also sample from that distribution. You can generate new X which belong to the same class. For example, now Leonardo da Vinci is not alive to draw more portraits like Mona Lisa, but given this Mona Lisa, can you generate these videos, right, which are basically many images? So it knows that it has to generate something of this sort, looking like this, but with different expressions. So if you know the distribution, you can sample from there and you can generate new images which look very much like this image. So these are called generative modeling, basically generating new data which comes from the same distribution as the given data. So popular approaches are generative adversarial networks, GANs, or variational autoencoders, VAEs. So this is the paper from where this demo has been taken. Okay, and then we have got more examples of generative modeling. So, you know, these days, this has become popular. Can the machine generate music? If I give the style of Beatles to the machine, means looking at the old compositions of the Beatles, can the machine generate a new composition, which is completely different, but still it is carrying the same taste of Beatles? Somebody will listen to this audio and will say, oh, wow, this looks like a new release from the Beatles. right? Or in Indian context, you can say, if I give some particular raga, let's say in Hindustani music, we have, let's say, Rag Bhupali. Can the machine generate a new composition which belongs to Rag Bhupali? Right? This is one example in Indian context. So the machine is generating music. Uh, so this is generative modeling. Now, another example which has become very popular recently in text or NLP domain, it's the GPT model. So what does it do? It basically can generate sentences which are meaningful, which look like somebody has written them. It can generate entire paragraphs, and you will not be able to make out whether it is some real person has written those paragraphs or some machine has generated those paragraphs. So this is also another example of generative modeling. Another dimension of generative modeling is when you know the PDF, means the probability density function. If you know the density function, can you sample from that PDF? For example, if I give you a Gaussian, let's say if I give you a uniform distribution, the random variable is a uniform random variable in the range 0 to 1. And you know, in Python or in any language, any programming language, you have toolboxes to randomly sample from uniform distribution. But now I ask you, can you sample from a Gaussian distribution? And so, okay, you will say, I have a function in my library which can generate from normal distribution also. But now if I give you a very complicated PDF and I ask you, can you sample from this PDF? How will you do that? So you will say, oh, I don't know how to do that. There is no function in my library to do that. But yes, you can go to these generative models and you can try to sample from those PDFs in a much more effective way. So this has got applications in particularly in physics. I have been working in area of physics, so I can share some insights from that area. But in many other areas also, like chemistry or biology or many other areas. But in physics, for example, you have to calculate observables given let's say in statistical physics, you have got many, let's say this is a very good example that let's say you have a boiling water, like water at a particular temperature. If I tell you the water is at temperature 50 degrees Celsius, how many bubbles are there in the water? You will say almost zero. But now I start raising the temperature and I ask you, at this particular temperature, how many bubbles do you expect? You will say, yeah, I expect, let's say, in this glass of water, maybe 10 bubbles. But as you raise the temperature really high, almost like above boiling point, more than 100 degrees Celsius, you will say, oh yes, this has got a really large number of bubbles. You know, the number of bubbles is increasing with temperature, but how many bubbles are there? That how do you know? So this you're trying to estimate the number of bubbles at a particular temperature. This is one crude example, but there are more refined examples. So, and also if I ask you, okay, another interesting question, how does the surface of water look like at this particular temperature? You will say, okay, at 50 degrees Celsius, it is just a plain surface. But as you are increasing temperature, the water starts moving, the surface of water starts moving. And let's say at more than 100 degrees Celsius, it will be really boiling and vigorously shaking. So I ask you, can you now simulate that water surface for me? So you know the physics or you know the equations which model that surface of water, but how to generate samples from that distribution so that you can get a nice video, for example, for an animation movie. So you have to sample from that PDF. So this is sampling, and there are Monte Carlo methods or many methods, variational methods which you can use, which we'll be discussing mostly, maybe some of them in this course. Okay, then next topic is little bit of shocking. Elon Musk said, mark my words, AI is far more dangerous than nuclear weapons. So AI can be really dangerous, and people have been showing concern about what AI can do and what AI what we need to be careful about when we do AI or machine learning. So you can see this is a really, something we also need to consider from this direction, from this dimension, that what we are building. So, okay, so mostly we see how to build something. Like in this machine learning courses, we learn how to make machine learning models, how to make particular classifiers or regression models. But we don't ask the question, what problems should we solve, right? We only ask the questions how to solve this problem, but we don't ask what problem to solve. So this comes under the from a different perspective, from the area of ethics. Is it worth solving this problem, or is it really, should I really invest my time in solving this problem? Okay, so Elon Musk has this kind of strong words, but these words mostly, when he says this, he pertains to this distinction, which is between strong AI and weak AI. Weak AI means when you are building models to do specific small tasks. For example, image classification is an example of weak AI, because the image classifier is trained to do image classification, and it is doing image classification. Even your Alexa or Siri is also an example of weak AI, because it was trained to do a particular classification task, and it is doing that classification task, nothing more than that. It is not trying to mimic human intelligence in that sense, like the complete full-fledged human intelligence or human reasoning or ability to make decisions on its own. So that is why there is a distinction between strong AI and weak AI. So when Elon Musk says this statement, he mostly is saying strong AI can be really dangerous if we make autonomous machines which can learn on their own, which can decide their own goals, and that can be very dangerous. Okay, anyway, so this was his point. But okay, this is a nice course from MIT by Professor Bernhard Trout. Let us see if we have time. Let us go through it. Short video.
We've been teaching ethics to MIT students for over a decade now, AI being a major aspect of that. And now we'd like to bring the question of ethics and teaching of ethics to young professionals who may not have been exposed to it or who want to understand the ethical issues around what they're doing. AI is considered to be one of the major future technologies that will, and actually is as we speak, influencing all industries, from healthcare, including pharmaceuticals, social media, all the devices that we use on a regular basis, and the interconnection among all of those. So the ethics of AI is essentially the ethics of technology related to society. Companies should send their employees to this class because it's really essential to the role that their employees play in society, in the country, and in the world as a whole. Because AI is going to have a major influence, it already is, it's going to have more and more of an influence. And there are concerns. Elon Musk here at MIT a couple of years ago called AI perhaps the greatest existential threat. On the
Hello, I'm sorry. I think there was some glitch. Okay, I'm sorry for the disruption. There was, I think the internet here went out in the lab. I will resume my screen share. Live streaming is still on. Okay, let me resume my screen share. Can you see it?
Technology. Based on that understanding, they'll be able to go back to their companies, introduce better clarity of the issues, help to think through company strategies on how they want to address the ethical issues of AI, and help to implement those strategies. So I'm hoping that students will come in the course, and through the course we'll get a better clarity of the foundational issues behind ethics of AI. We'll certainly understand those within the technologies themselves. We'll call it a range of technologies. And we'll go out to be more informed and make better decisions and help society to make better decisions about AI.
Okay, so yeah, so so the message of this video was that it is not just important to learn the technology, but also to learn how to utilize that technology so that we know what we are making and it is whether really helping the society or not. So okay, AI and ethics. Should we make versus how to make controversial systems. So there are many systems which could be controversial. For example, who will win the election, right? Or actually, I was inspired by this topic. I was in University of Maryland, sorry, not University, in Queen's Mary University in London. We had a conference there on AI. And I was just socializing and meeting some people. So one person, he came, one person, he just introduced himself and he said he comes from a betting company. Betting company means it's like a gambling company. And I asked him, why do you need AI? He said, we need AI to make the customers stick to the screen more and more. Means they want to make strategies, they want to make technology such that his betting company could earn more money. Basically, people, they don't quit the game and they keep playing and keep losing or putting more money into the system. So okay, so means I was surprised though. Do I really want to work in this towards this kind of goal? So anyway, so this is the concern that should we make certain systems? So we should be thoughtful about using the technology. And okay, and also another implication that our feature and design choices, they make beliefs and values for people or the users. For example, if in a system, if I choose some design choices, imagine your Fitbits. Your Fitbit, it tracks how much steps you have walked or what is your heartbeat, heart rate, what is your pulse rate, and all these parameters are monitored by the Fitbit, and based on that, it gives you some suggestions. So, and somehow it tends to reduce your understanding of your health to certain specific parameters, which are very, very reductionistic, which are very, very small, very, very narrow. So it gives you a good image of your health, a good indicator of your health, but these indicators are very, very narrow and they just capture a very small portion of your actual health. So users have to be very careful that their health is not just about how many steps they have walked or what is their pulse rate, but so and this so and also nowadays, there are apps which can suggest you what you should eat, what you should not eat, and so we tend to narrow down our choices, and basically the choices of the designers of AI, they kind of have an impact on how people think and make their own belief systems. And then we know that AI systems are not objective and free from biases. They also have their own inherent biases. For example, racism, sexism. It could, because where do the AI systems learn from? They learn from data, and if the data is biased, it has some inherent biases, and the AI system has not learned to nullify those biases, then those biases will also reflect in the systems that we make. So this is an important concern. So a good example could be, for example, you are in a building and the building has got robots which are guiding people. Suddenly you see that the building is on fire. Now, who will you trust? You will trust the exit sign, or will you trust the robot? Let's say the exit sign says that the exit door is in this direction, and the robot is saying the safest way is this way. So whom will you trust? So they kind of limit us. They are not means you have to now the question comes on the makers of AI. Should we make such systems, or what kind of care should we take? In what ways should I train my system so that it is avoiding these mistakes? And then AI systems can undermine our free choices. Imagine you're using YouTube. The YouTube gives you certain recommendations of next videos, and it kind of creates a bubble for you, and you try to, means you are kind of confined in that bubble, and you don't see the world beyond that bubble. So your AI system, like Google or YouTube or Spotify, they create a bubble for you, and you are kind of caught in that bubble. So if you don't believe, you must have heard about Cambridge Analytica. They kind of how they changed the results of an election. Means so these are some serious concerns. Also, Microsoft released one chatbot, and within hours they had to remove the chatbot because it had learned all the garbage language from users. Means all the filthy words it had learned. So means okay, so there are so many concerns, so which we can study from this perspective. Okay, now the way forward in AI. Okay, so this is now what I discussed until now was all the current state of the art, and also about what people have been working on, what are interesting problems in machine learning. But now what I'm going to discuss is, okay, let's think a little bit out of the box and what we can do different, which has not been done until now in machine learning. So our current AI is, so what to learn, it is given by humans, right? Humans will tell you learn speech recognition. These are the phonemes. This is what the machine has to learn. And then why to learn? Why does a machine learn something? The objective function is given by the humans. That's why it learns. When to learn? When should the machine learn? That schedule is also, training schedule is given by humans. For example, in big companies like Alexa, Google, Apple, they have their schedules that the data is all brought together, and the engineers, they schedule the training in a way that, okay, it will take 5 days to train the system, and then on the 7th day it will be released. The latest version will be given to the users for using. So and similarly, how to learn that model and update law is also given by humans. But now let's look at human intelligence. Do we learn in that way? What to learn? What should I learn? Why are you learning this course? Nobody programmed you to learn this particular course, but you are learning it because you have a semantic goal. For example, you have a goal that I want to earn my degree. I have to complete my credits so that I can get my degree on time. Now, why that goal? That you ask yourself, why do you need the degree? And then you will say, okay, I have to maybe I have to get a good job. And by that job, you have certain other reason to choose that goal. So basically there is a hierarchy of goals, and you are trying to achieve a particular goal. So what to learn is decided by your semantic goal, not by any objective function as in a machine. Why to learn? Why to learn? Because you have your intrinsic belief, because you believe that if I do well in this course, I will get a good grade. And if I get a good grade, I will get a good CPI, and good CPI, good knowledge, and I will be able to crack good interviews. I will be able to go to a good job or a good PhD position or a good something. And you have your intrinsic belief system, and you think, okay, if I do this, then there are better prospects of my survival. I'll be happier, right? So why to learn? And when to learn. So when do you learn? Okay, this is something you can debate about it, but I'm just presenting one possible viewpoint. We learn when there is crisis. When there is exam, then we study. When there is a fear of losing, then we learn things. For example, if there are no exams in the course, it is very unlikely that I will learn something. Means I will learn something, but not that much as much I will learn when there is some crisis. Means crisis kind of makes it more likely that I want to learn something. Like you see these days, Corona has come. It's a crisis time, so everybody is learning, trying to model quickly, trying to bring out vaccine quickly. Similarly, you can see when the World War II happened, most of the innovations in science and technology, like a boom came uh, during the World War II. It was a crisis time. They had to save their lives, and so many technologies, radar technology, even many advances in machine learning were done during that time, like Monte Carlo sampling. All that was invented in World War II time. So when to learn? When there's crisis. This is how humans work. And how to learn? So we don't learn sample by sample and make classifiers or decision trees in our mind. No, we have a semantic organization of the world. So for example, uh, um, we have semantic organization. Means if you ask me what is a neural network, I won't tell you the equations of neural network, but I will tell you a semantic understanding. Neural network is a classifier, and it is a kind of, you have a space, and it is trying to build some discriminators or some lines, and dividing the space into regions, and then mapping those regions to certain classes. So I have my own semantic way of understanding the whole concept, which is not how the machine learns. And I can give you more examples on this. For example, when you learn a new game, for example, the game of chess, or the game of what is called the breakout, which means there is a bat in the bottom which is moving left and right, and the ball is coming and hitting, and there are bricks which it breaks, and when all the bricks are broken, when the match is over, means you win the match. You have to keep the ball above this bat and then hit all the bricks so that you get points, right? That is one game. And then there's another game where you have ping pong. You have two paddles. They're not moving, but they're not moving horizontally, but they're just flipping like this. And with that, in the game of ping pong, the ball is falling, and you have to just hit it properly so that it does not fall down, but it hits all the objects and gains point in that way. So if you know one game, you can very easily learn the next game. But machines, for them, it is not that simple. I mean, for machines, these are two separate games. They have to be learned separately in their own with their own data. So there is no semantic organization of the world in current machine learning. So everything is learned from scratch in a brute force way. It operates at the pixel level, not at the object level, learning end-to-end learning, but no meaning intermediately. It does not know that these are bats which perform certain actions in a semantic way. Okay, so, and this is a video. I will skip this video for the interest of time. You can watch it later. Failures of current ML. And then there is no common sense knowledge in current ML, and Gestalt principles. These are psychological principles that if there is some rod, some obstacle, and there is some object, you know that these two ends they belong to the same object. And then this is adversarial attacks. So if you give this image to a network, it will say this is a starfish. Why? Because this image is trained to fool the network. So just like see this. So this is a panda, and you give it to um, a common image recognition model. It will say, yes, this is the panda with 7.7% confidence. Very good. But now I design this noise in a particular way. I design it in a way that if I add a small amount of this noise to this image, visually it does not affect anything, but the model thinks it is a gibbon. It's another animal, a different animal altogether, with 99% confidence. So means a small amount of noise, but specifically designed noise, can change the predictions of the model drastically. This is called adversarial attacks. This is not something new, but okay, I just added it. And but there are two videos which you can watch. One is by Josh Tannenbaum. He's a professor in MIT, and he tells how to make machines that can see, learn, and think like people. And another video by Yoshua Bengio. I hope you all know him. He's a very popular figure in machine learning, deep learning. One of the pioneers in deep learning. And he says system 1 deep learning and system 2 deep. He has defined his own terminology, saying that how deep learning needs to transition in a way. Okay, so these were my slides, but let us quickly now discuss about the logistics of the course. Let me open. So the course homepage is, okay, let me share my Chrome window with you. Okay, so in teaching in advanced topics in machine learning, this is there. Okay, so here you have the course webpage. There are the TAs are listed here. You can contact them. Course objectives, prerequisites, you already know. These are the topics roughly which we'll be studying. We'll start with some programming because, machine learning is primarily programming, a lot of programming involved. So we'll study something about data structures and algorithms. Some of you might have done these courses before, no problem. So you can make use of those courses. But for many of you who have not done these courses, these few lectures may be useful. Then we will be studying about deep neural networks. We'll be focusing mainly on two broad topics. One is generative modeling. In generative modeling, we are studying Monte Carlo sampling, variation autoencoders, GANs, normalizing flows. Another area is time series modeling, in which we'll be studying dynamic programming, hidden Markov models, LSTM, recurrent neural networks, and CTC learning. So these are the contents of the course. But of course, you are welcome to suggest or bring in more topics via your projects. There are the topics which I discussed, like attention models, few shot learning, domain adaptation, explainable ML. All these will be discussed in short, and you can elaborate them in your projects. So we will have projects. So the grading will be like this, roughly 40% for assignments and quizzes, 25% mid-sem, 35% end-sem. This end-sem could be a project. I'm thinking of giving it as a project instead of a written exam, but we will see as we go. Okay, and then we will have projects. So you will be doing projects in groups of 2 to 3 students. I would suggest you form your groups. Soon the TAs will be asking for your group choices, basically your groups. You can submit who is the group, who are the group members, and who is the group leader. So we will be generally, group leader is only for the purpose of communication. We will be, let's say if there is any communication, any information we need to share, we'll just share it with the group leader, and the group leader can tell everybody that this is the thing. Okay, and then the references, there are some good books, like PRML by Bishop is a very good book on this area. And there are other books as well. This is a recent one, Deep Learning by Ian Goodfellow, Yoshia Bengio, Arun Corville. So these books could be referred, but we'll be mostly focusing on some research papers to deal with these topics. Oh, that's it from my side. If you have any questions, feel free to ask. Any questions at this stage? Okay, I will just repeat. You form your groups, group of 2 to 3 students. 3 students is good. If you can form groups of 3 students and just make your groups and keep them ready. Our TAs will send out a notification where you can submit your group names of the group members. Okay, then if there are no questions, we can stop here. Where can I get the list of registered students for making groups? Is it not available on MOOCIT? On MOOCIT, don't you have lists? Can you not see all the registered students in MOOCIT? If it is not there, I can float the list. I can give you the names and email IDs of all the students registered for this course. Is that all right? Anybody has any objection on this? Okay, fine. Then I will share the list, or I will ask the TS to share the list. Okay, I will share it. Fine. Any other question? You can always ask your questions in the MOOCIT forum. Does this course require strong background in signal processing? The answer is little bit knowledge will be helpful, but we'll be using libraries for signal processing. Let's say LibRosa library for audio processing, and maybe OpenCV or something can be used for image processing. So you may not need that much knowledge of signal processing, but yes, some intuitive understanding has to be there, like what is frequency, what is spectrum, what is spectrogram. These things are definitely required. I think go through the MLSP course. MLSP course has got some DSP lectures. You can go through them. Yeah. But yeah, we don't need a very strong signal processing knowledge as to, for example, what are Butterworth filters, or designing some filters and pole zero filters. All those things may not be required. Okay. Thank you. Any other questions? Otherwise, we can stop here. Okay. Okay. Thank you very much. Goodbye, everybody.